developing next-generation research and technology, facilitating connections between AFRL industry and academia, unlocking innovation through a culture of collaboration. This is the AFRL Regional Network Midwest.
My AFRL Hub project is to investigate the impact of shockwave boundary layer interactions on surface heating, and in particular, what if the surface was thin like a flight vehicle, and that surface heating caused the panel to bulge and thus impact the fluid flow that's causing that heating.
When you place the cone flare in high-speed flow, you have a bow shock that forms at the nose tip, you have a boundary layer that develops in the conical forebody, and it thickens as it approaches the cone flare junction. Under certain conditions, the boundary layer may separate, and you'll have a separation shock. Boundary layer eventually will reattach on the flare, and you'll have a reattachment shock. And in between separation and reattachment, you have a recirculation bubble that could be unsteady. Downstream of the reattachment shock wave on the flare, the pressure is extremely high, and the boundary layer is relatively thin, so you have higher thermodynamic heating on the flare.
This coupled problem is known as a fluid thermal structural interaction, and it's a complex challenge impeding our progress to successful hypersonic vehicles.
First increment of the AFRL Hub project was to first perform computations and compute a thermal deformation field. Then we would superimpose the deformation field onto the flare and fabricate a deformed flare so that we could experiment with it in the Notre Dame Mach 6 Large Quiet Tunnel. We tested the model in the AFOSR-Notre Dame Large Mach 6 Quiet Tunnel. For the experimental setup and instrumentation, we collected simultaneous surface and off-wall measurements. We collected infrared thermography. We had 4 PCB pressure transducers mounted on the conical forebody to align the model with the free stream flow. For off-wall measurements, we collected simultaneous high-resolution background orange Schlerend and high-speed background orange Schlerend. This slide here compares heating distributions for the conical flare on the top row and the deformed flare on the bottom row. We can clearly see by comparing the conical heating to the deformed heating that the heating distribution is no longer axisymmetric, and the peak heating magnitude is different as well. This slide here superimposes the off-wall measurements with the surface heating measurements. From the off-wall measurements, we can see the bow shock, we can see the separation shock wave, we can see the reattachment shock wave here at the flare, and most interestingly, we can see where reattachment is. Downstream of that point, we have the higher dynamic heating characteristic of the shockwave boundary interaction.
Such deformations have occurred previously on high-speed vehicles such as the Valkyrie seen behind me. As part of this research program, we conducted an experiment at the AFRL Mach 6 Ludwig tube. This experimental campaign allowed us to use the same Rotex-T model that was tested at Notre Dame previously to collect data at a facility with a different free stream noise environment. Similar to the tests that were conducted at Notre Dame, IR thermography was taken of the cone and the deformed pedal of the flare. This diagnostic allows for measurements of heat flux in the regions that were imaged, letting us directly compare the results from the 2 different facilities. In addition to IR thermography, high-speed self-aligned focusing Schlerend, or SAFs, was taken at AFRL. It allows for density gradient measurements to be made across a narrow depth of focus, avoiding the large integration distances that occur for traditional Z-type Schlerend. However, it was a difficult technique to implement due to the high sensitivity of the diagnostic to vibrations and the challenge in aligning it. Preliminary results from this experiment support the conclusions made from the Notre Dame tests, showing that the deformation along the flare appears to pin reattachment. SPOD analysis of the Schlerend also shows there does not appear to be significant changes in the instabilities present for the different deformation heights.
Hi, my name is Nolan Little, and I work in the Computational Aerodynamics and Flow Physics Lab here at Ohio State under Dr. Dewan. And we took a computational approach to studying how the surface deformation on the Rotex-T cone flare affects reattachment heating. So we did 2 direct numerical simulations here, and we did one with an undeformed flare and one with a max deformation of 1.6 millimeters, which corresponds to the more deformed of the 2 pedals used in experiments. And both of these domains span a full 90 degrees, which covers a whole pedal that would have been used in the experiment. Now looking at the instantaneous state, remember we have the undeformed case on the top and the deformed pedal on the bottom. Both cases are going to experience some streaking more as time goes on when this global unstable mode develops over the flow and creates more of those red hot spots in the domain. Here we can see a side-by-side of just the flare. We can kind of see as these videos go on that this streaking occurs earlier in the deformed case on the bottom than it does on the top in the non-deformed case. This earlier streaking kind of seems to point to the global mode growing faster with that deformation. So the deformation kind of makes the flow a little more unstable, which can cause a more turbulent or a transitional flow that we might not see in the undeformed case. But the undeformed case does eventually have these streaks grow to numbers that rival that of the deformed case, but overall the deformed case has higher peak heating.
So understanding how structural deformation can affect the local loading is crucial to both the design and life prediction of high-speed vehicles. Now, our experiments aim to study aspects of this problem by focusing on how local deformations can affect the peak heating associated with shock boundary layer interaction. An exciting next step of this work is to model our experiments using high-fidelity fluid simulation. This will shed insight into the effects of facility noise levels and allow us to extend our findings to quieter, more flight representative environments.